Okay, so yeah, let's move to the last talk of the day. Great pleasure to have Itai Benjamini from the Weizmann Institute. So he'll be telling us about bounded harmonic functions on graphs. Anytime you're ready, start. Yeah.
Okay, so I will start, since I thought initially it's a percolation, first passage percolation conference, so I will start with a comment about percolation that will get me into harmonic functions and geometry. So I want to first start to define two Boolean functions. So say I have xi, these are Bernoulli, say, okay, so I have a sequence of xi, x1 up to xn of Bernoulli random variable, and I will define two natural function of this sequence of IID random variables, and we'll try to manage with this. So I have this sequence of Boolean functions, and I will define two Boolean function. One of them is very natural. It's just I will take the sum of x1, xi up to n, and I will look at the event that say this is, let's call it majority, that is the event that this sum is bigger than 0. So I just have a collection of n bits, independent symmetric bits, and I'm just looking at the event that the total sum is bigger than 0. This event, I will call it majority, and another more sophisticated event is the event I will call percolation, or maybe crossing, is the following event. I will take an n by 1 by n square. So, well, here I need n square bits, and for each edge, I will just put, for each edge e, I will put here xe. So I will just place the bits on the edges. So if I can, if you want, if it's n, I can just square root and square root n. But anyway, on each for each edge in the grid, I throw a coin to decide if the edge is written here +1 or -1. And the event I'm looking for, the event crossing, is the event that I have a path of edges. All of them are written 1 that connect left to right. This is the event of crossing. Now, my question to you is, so I have crossing. I have crossing, and I have majority. Now someone is coming, so I have these two events, say crossing, let's say n with n bits, and so it's a square root n by square root n square grid, and say majority on n bits. And now what I'm coming, instead of giving you the sample, I'm noising the sample. So to each edge I go, and with probability epsilon, I fix some epsilon, bigger than 0, and I go to each xi, and I refresh it with probability epsilon. So xi epsilon equals xi with probability 1 minus epsilon, and the new version with probability epsilon. So yi, where yi is independent, identically distributed. So I'm just going and I'm refreshing independently each of the bits. Now the noise sensitivity question is, I'm taking these two events and I'm asking myself, say I tell you that majority happens. Say I tell you that the event majority happens, so the sum of the xi from 1 to n is bigger than 0. So say I tell you, so sum xi up to n is bigger than 0. So I tell you this event occurred. Now I refresh it, and I have the refreshed or the noised. Sorry, I have the noised bits, and I'm asking whether conditioning on the events occurring before, what can I infer? Is some information lasted the perturbation, or all the information is gone? And the same question I can ask about the event of crossing. So say I tell you that I pick the sample of the bits on the edges, and then I'm actually observing, and I see there is this open path connecting left to right. Now I'm noising the sample, and I'm asking, is typically like conditioning on having a crossing before the noising, what does it tell me? Is any information last for after the noising, after the perturbation? So do you want to vote? I don't know whether we have a procedure here to vote. Which event you think is more stable, the crossing event, the crossing event, or the majority event? Which event you believe is more stable to this epsilon perturbation? And by the way, let me tell you, so I mostly hear myself, I don't hear anyone, so please feel free to ask questions and interrupt any moment. And so I don't know if we conduct, I don't know, raise hands, so I don't know how can we conduct a vote, but which of the two events you think is more sensitive to noising? For which event after the noising, roughly no information last after the noising? Okay, so let me tell you the answer. So apparently, majority is very stable because, or what is very stable? Let's see. So assume majority happens. That we threw the n coins, and we know that the total sum is bigger than 0. Then typically, it will be of order 1 standard deviation. So it will be typically by the central limit theorem. It will be order square root n more 1s than 0. Now, if we noise epsilon of the bits, then what does this tell you? That we will, from where we are, which is typically square root n away, we will move epsilon square n away from this point. So if we were positive, likely we are still positive. So on the conditioning on majority, if I tell you that I now refresh say 1,000, 1/1000 of the bits, then very likely if n is sufficiently large, then that we are still a majority still occurred. But now it turns out that the event of crossing is highly sensitive. It turns out that the crossing is highly sensitive. Crossing is highly sensitive. That is, if I tell you that I noise epsilon of the bits as n goes to infinity, then telling you that before the noise actually percolation occurs, it hardly gives you any information. So on a typical configuration, the noise is almost like resampling completely. And since this result, it's a joint theorem with Oded Schramm and Gil Kalai. Schramm from 99. It started a little industry, and the state of the art is by Garban, Pete, Schramm, that they proved that actually the critical exponent is 3/4. So if you noise n to the 3/4 plus epsilon of the bits as an increase, then you are uncorrelated. So they found the exact so it's the exact noise exponent, and since there were a lot of progress, and there are now even shorter proofs, and the theory of noise sensitivity of Boolean function is rather developed. Now, I was struggling, I was thinking, can we make some sense in this useful notion of noise sensitivity in the context of random walks on groups? And so I suggest the following. So say we have a gamma finitely generated group with, I don't know, generating set S finite generating set. So and then we have a random walk that we have, xi is belong to S, and say chosen uniform from S. If we take we have some measure on S, and then we define the corresponding random walks, and that we start, I don't know, to take the product of the elements. So we have x1, x2, and then we define, Sn or SRW, or well, and this is where just we take the product of the element from the generating set. Each one chose independently according to the measure, and we get the distributions in UN is the distribution, say, this is the distribution of SRW, and this some distribution on the element of the group. So this is just a simple random walk. Well, if the measure is uniform, I don't know, then, and if the set, usually we take S to be finite and symmetric, then we get uniform measure, and this gives us simple random walk on the group. And so, for example, we can take, well, I guess everyone knows what is simple random walk on a group, on a free group, on C, and so again, please ask question or comment if I'm going on something a little bit quickly. So what is the idea here? What will be noising? Noising will be, we have this product x1, x2, xn, and we can go to, we have our epsilon bigger than 0, and we can go to this product and refresh each bit independently with probability epsilon, and replace xi with yi, which is independently chosen. With probability epsilon, we pick an independently chosen yi from the generating set S. So we have SRWN, and we have or let's call it SN, and we have SN prime is like the noise version. Now we want to ask for which groups finitely generated, for which groups Sn goes to infinity, Sn, and this is the informal question. Sn is asymptotically independent of Sn prime. So there are several definitions, and you can ask this notion of independence, you can ask it in different norms and all that. And this is something I looked at it with recently with Jeremy Briussel. Briussel. So we looked at this, and here there are several notions of noise sensitivity for random walk on groups, and the one I think is the most canonical, which I will now mention, is the following. So let's say mu n will be the distribution of the distribution of Sn, and the mu n prime, this is the distribution of Sn prime. And so what we can and we want to know how much these two measures are correlated. So we should look, we say, I don't know, G gamma, the group, or with this generating set is noise sensitive if for any epsilon bigger than 0, we look at the total variation distance between, we take mu n times mu primes n minus 2 copies of, let's check now, 2 independent random walks. So y, let's, I don't know, we'll have yn and zn, 2 independent RW, just like the previous one, and we have the mu for y and times mu of z n. And we want to say that this one, as n goes to infinity, this goes to 0. So just we want to say that if I tell you in words, or first I will say it in words, we have one random walk, and we have the distribution of where the walker is at, and we have now we take the path and we perturb it a little bit, and we have the new point. And we are asking whether these 2 points that were sampled that way, this is this measure, are actually in total variation distance. It is if we just take two points, each one was chosen according to an independent random walk. So just please tell me if I'm clear, or at least more or less clear.
Yeah, this is fine.
Okay, thanks. So now examples. So let's first ask, is Z with the generating set plus minus 1 noise sensitive? So I have one random walk. If it walks for n steps, it's exactly like the majority function. So it's exactly what I started before. I have the majority function. So the position of I take the random walk. It's a sum of plus random, say 1/2 plus minus signs, and then I tell you that the random walk is positive, is a positive half line. Now I perturb it a little bit. Then from what I was saying before, very likely the new walk will be also in the positive half line. So if I tell you that before the noise I'm here, it's after n step I'm around square root n somewhere. Now I noise it, then very likely I will also be positive. So condition on the first walk to be positive with high probability, the second walk will be positive. So it doesn't behave like two independent random walk on the line, which the fact that the first one is positive doesn't tell me anything about the second random walk. So now this was one extreme, the Z. So the other extreme is another question is F2, the free group, on two elements. It's noise sensitive. Okay, it's really a shame. I don't see you and I don't hear you. Well, I just hear myself.
It should be noise sensitive, right? Because if you perturb a little bit, you're going very far.
Sorry, what you said? It's not noise sensitive.
I mean, yeah, if you perturb it a little bit, then then the random walk should go very far from the original one, right? On a tree.
Oh, well, okay. So I have one random walk on a tree that went very far, and then I noise it.
Yeah.
So the new sample? What information from the old sample will last? So you're actually right. F2 is not noise sensitive. And here is the argument. So here is the tree. I don't know. So let's draw it like this. Okay. So say I tell you that the first random walk is here in this quadrant. It's somewhere here. After n steps, it is here. What does it tell me about the second walk? The probability it's here is
it's also on the quadrant. Yeah.
Is slightly bigger than 1/4, because most likely, the first step, the first few steps were unaffected. The random walk went somewhere far away here, and the point about random walk on the free group is that the position of the n step in 4. Okay, let's the n step of SRW on F2, so is uniformly correlated with the first step. So there is an information in the first step. Now, if I noise, and I will come back to the, but so if I noise very few, the first few steps with high probability, the first few steps will be the same, and then they are with high probability determine your fate to be stuck in this tree. So, and the Kajmanovic-Vershik in the 83 paper, this is Kajmanovic-Vershik, they studied harmonic functions on group, and their criterion was that a group admits non-constant bounded harmonic functions. So this is a finitely generated group admits, and I will define harmonic function, admits non-constant bounded harmonic functions if and only if the simple random walk has a positive speed. So the distance between the origin and say Sn, or I don't know how to define it, Sn is of order, in expectation even, is order Cn. And this, they proved, is equivalent to having non-constant bounded harmonic function. And just to say, f from vertices of a graph to R is harmonic if for all V, some U neighbors of V, Fu over the degree is that the average of the value of the neighbor equals the value of V. Then it is harmonic. And then there was the question, when does a group, when it admits non-constant bounded harmonic functions, and we say a graph or a group is Liouville. This is from Liouville theorem. If it admits no non-constant bounded harmonic functions. Now, Kaymanovich-Vershik gave this criterion that on a Cayley graph or for finitely generated group, with respect to the averaging of the random walk operator, the graph or the Cayley graph admit non-constant bounded harmonic functions if and only if the random walk has linear speed, or gamma is non-Liouville, if and only if the support mu_n has a linearly growing entropy. So what is linearly growing entropy is that the information to describe, this is now we move to describe entropy in terms of information, the number of bits that need to describe the position by time n is of order n. So in particular, in another word, is that there is information about the finite position in every steps. And in particular, the first step is correlated with the position of the last step. And in noise sensitive groups, this cannot happen. So in particular, what we get is we get from the example of Z, and from this example, we get that, I went very, very fast, but we get that if gamma is non-Liouville or admits a homomorphism to Z, then gamma is not noise sensitive for the simple harmonic. And actually, we can relax the admittomorphism if it doesn't admit a finite index group that admit a homomorphism to Z. So essentially, our first open question, our first open problem is assume a G or gamma, sorry, is Liouville. And there is no finite index subgroup of gamma group homomo to R or Z is gamma noise sensitive. So we don't know. This is our first big question. I will mention a couple of questions today. This is question 1. Question 2 is, we believe, for example, such a group is now, how do I write Grigorchuk? Grigor, I don't know, something like this, I hope, is the Grigorchuk group noise sensitive. Note that as group people in group theory explained to me that a little bit the Grigorchuk group is a little bit like the lamplighter over Z. So I don't know how many. Should I tell what is the lamplighter?
Yeah, that would be good. Yeah.
Okay. So let's just make a picture. I will describe to you what is the lamplighter over Z. We have Z. We have finitely many ones. We have a word from it. We have a function from Z to 2 elements. So and then everything is 0. Say this is the origin. So a vertex in the lamplighter graph consists of a word in 0 and 1s over Z, and the position of a lamplighter. So it's just a function. An element is a function from in 0 1 to the Z, and a number and some X in Z. These are the vertices. These are the vertices, and what are the edges in this graph? And by the way, these Fs, they have finitely many ones. So these are the vertices, and the edges is what we can do is some V of this form is called, if V U is in the edges of lamplighter over Z. So this means that either you obtain from V by switching the bit at the position of at X, at the position of the lamplighter. So it's either we have an identical F, except at point X, which it's you swap, you replace between the 0 and the 1, or you can just move X to +1 or -1. This is the lamplighter graph. Now, if you do simple random walk on that thing and then you noise it, you believe that there will be hardly no information in the scenery of the 0 and 1s. This will be totally uncorrelated. But the only thing that might be indeed correlated is the position of the lamplighter. So this is the homomorphism to Z that we have, that sort of make this group to be noise stable. But in some sense, the Grigorchuk group is a little bit like lamplighter without the lamplighter itself. So one question is, so we have this question 1. I'm sorry that I don't have a blackboard and we don't have each time you see what I'm talking exactly now, but I hope it's okay. And so we suspect that maybe a group is noise sensitive for the random walk if it doesn't admit a finite index subgroup with a homomorphism to Z, or it's Liouville. Now, so in particular, we would like very much to know if the Gregorchuk is like that. Like question 3 that we don't know is it a group property? So I mean, if you replace the one generating set, a symmetric generating set with a uniform, say, a measure, by another generating set with a uniform measure. So how sensitive this property to that? And this brings me to now to speak about harmonic functions. So I wanted to get to harmonic functions from percolation somehow. So via noise sensitivity, and noise sensitivity is for random walk is related to Liouville property. So now we ask whether it's a group property. So how sensitive it with respect to all kind of equivalence on group, like for example, different generating sets. So this leads us to the following question, which is a long-standing open question. So a long-standing open question is the Liouville property invariant with respect to different generating sets. And more generally, if we have if gamma 1 and gamma 2, or let's say 2 calligraphs, if G1 and G2 calligraphs, G1 quasi-isometry to G2, are they Liouville together? This is a long-standing open question with many people working on it, and there are some classes. For example, it follows from the work of John Nash that the calligraph so even a question related to that is stability of the green function under quasi-isometries, and John Nash proved that on ZD, or then the decay of green function is equivalent under quasi-isometries, under rather general quasi-isometries. But by the way, should I define what is quasi-isometry?
No, I think most people are familiar with it. Yeah.
Okay, if someone, unless someone requested, I'm not defining what is quasi-isometry, but now I want to entertain you for general graphs. For general graphs, Liouville property is not quasi-isometry. So actually, Royden, was a complex analyst, he observed that transients of simple random walk in the 50s. He observed the transients of simple random walk, it's just equivalent of having a flow with one source and no sinks, that the gradient is in L2. This is a quasi-isometric property. He observed it for for manifold, but then so transients of a simple random walk on bounded degree graph is a quasi-isometry invariant. And the question was, what about the Liouville property? So in the mid-80s or 87, JDT, Terry Lyons, not Russell, Terry Lyons constructed a rather involved counterexample, and now I want to entertain you. At least you will see something entertaining in the talk. I want to show you a cute, a very easy example of a general graph, which is very far, unfortunately, from a Cayley graph, for which the Liouville property is not quasi-isometric invariant. So the example will be like this. Say I have a graph, some infinite bounded degree graph, and I have a set, absorbing set, I will call it, that absorbs. I have a set A that absorbs the random walk. That it has the property that if I do random walk, it bound with probability 1, it eventually enter this set and stay in that set forever. But now, say I do a quasi-isometry and I get a set B, disjoint from disjoint from B, that after the quasi-isometry, the random walk is sure to absorb in B. Now, your first exercise in the talk is think if you have in mind such a graph, that there is a set that absorbs the random walk, a non-trivial subset of the graph that absorbs the random walk with probability 1. But after I perform quasi-isometry for the graph, there will be a disjoint set that absorbs the random walk.
A branch of a tree?
Yeah, exactly. Not a branch of a tree. So this G,
yeah, I mean a subtree.
It can be just a binary tree.
Yeah.
And say we'll take A in the binary tree. Each vertex in the tree, it has a name. You know, whether I turn left or right from the origin. So say 0, 1, 0, 1, 0, 1 will be the vertex that I go first to the left, then to the right, then to the left, then to the right. And so each we can give naturally name to the vertices of the binary tree. And for the absorbing set A, I will take A to be all A. All vertices with epsilon, I will define with 1/10, 1/10. With number of ones over number of zeros in the names, in their names, is between 0.4 to so it's between 0.9 and 1.1. So this will be all the balanced vertices. Is it clear?
Yeah.
That all the vertices with relatively balanced vertices. Now, what will be so this is A. Again, sorry for my poor technology. So this was A. These are the relatively balanced vertices. And B, I will take B all vertices with a number of I don't know, ones over a number of zeros, this is a gadol, bigger than, sorry, than, I don't know, 1.2. So these two sets are disjoint. And what I can do if I have the binary tree, if I have the binary tree, note that, say, the random walk is here. Or if I have a general tree, a transient tree, and I know that the random walk here and is about to absorb in this subtree. So the probability it will absorb in this subtree relative to this tree, so say I condition it to go up here and not return, then it will be a ratio of the resistances. I view this subtree as an electric resistance and this subtree as an electric resistance, and if the resistance here is twice, then the probability it will absorb, then this one, the probability it will absorb here, is twice as bigger. So the quasi-isometry I can do, I have my binary tree. Now I take all the zero edges, the edges that turn left, and I just divide each of them to, say, 10,000, whatever. I replace them by a path of length 1,000. So this graph is quasi-isometric to the original tree because 1,000 is finite. But now, if I'm here, and I know that from here the random walk will go to infinity, the electric resistance from here is much larger than the electric resistance from here. So very likely, I can make that the probability that it will absorb in this subtree much higher than it will absorb in this subtree. So therefore, I can, by making this, I can make this happen for the random walk, this condition. I can make the random walk to get absorbed in this set by just making this quasi-isometry. So now, so I have my binary tree. Now I have this set A. This is A. Now I take here Z4. This is Z4. This is the x-axis. Say this is just x 0, 0, 0, x in Z. This is A. I take some bijection between A and this x-axis, and I put an edge. I put just an edge in some, I take some bijection from this countable set to this countable set, and I put one edge between any vertex on the x-axis in Z4 to a point in A. Now, this is the example. Someone is willing to tell me why the Liouville property is not quasi-isometric on this graph?
I mean, the random walk gets absorbed in Z4 again and again, right? And Z4 is, I mean, has a Liouville property.
Yeah, but then so before on this graph, before doing the quasi-isometry, this is just a regular binary tree. Then I know that no matter where I start random walk, it will get into A. Well, no matter on the tree, and then it will try jumping here. It might return, it might stay in A, it might jump again. Eventually, since I have 3 codimensions, eventually it gets absorbed in Z4.
Yeah.
And Z4 is Liouville, and actually 2 random walks in Z4 can be coupled. So this graph is Liouville. But now, say I do the quasi-isometry I suggested before. Then after doing, I have this B appearing after making this quasi-isometry. Now, random walk on the tree is likely to absorb, if it starts in B, it with hyperbolic stay in B. And now, on the other hand, if I start deep in Z4, it will not hit the axis at all. So I have a non-constant harmonic function by just defining what is the probability I will absorb in Z4, in the Z4. So actually, I have in this example, I have a two-dimensional space of at least two-dimensional space of harmonic functions. So this is, I think, a simple example showing that the Liouville property is not quasi-isometric invariant for general graph bounded degree graphs, but what about K graphs? This is a long-standing open problem. Now, okay. Okay, I want to move on. So I see that I don't have time for what I planned. So I want just to say another difference between groups and general graphs is the following: if G gamma is non-amenable, and I don't have to define what is non-amenable because it was mentioned at least already in previous talk, finitely generated Cayley graph, then gamma is non-Liouville. Now, okay, here is another example. So actually, Yao, STR, ask in the context of Riemannian geometry. Assume you have a bounded geometry metric, simply connected metric on R3, which is non-amenable or have a non-trivial spectral gap. Is it non-Liouville? So for Cayley graph, we know that non-amenability implies non-Liouville. He asked whether it holds in the category. He wanted some non-homogeneous categories, so he suggested bounded geometry metric, Riemannian metrics on simply connected Riemannian metric on R3. And the answer is no. So with Janko Chow, the late Janko Chow, we constructed a counterexample. So, but here, what I want to show, this is very complicated, and the Riemannian setup is annoying for me. But if we just want to fill, we ask a naive question: G bounded degree graph with a positive Shiger constant is G non-Liouville. Guesses, anyone? Actually, I told you actually the answer. So what is non-Liouville? From what you know naively, you know that from hyperbolic geometry, you know that what is non-Liouville is that the fact that you have many ways to go to infinity. That you can, there are different directions to go to infinity. And the question is whether non-amenability implies that. So surprisingly, in groups it does, in somewhat not that geometric, maybe simple way, but this is this entropy growth but just in the category of graph with non-amenable graph, this is not the case. And let me show you what is the trick. And I hope I have like 25 minutes, right? Because I want to get to a punchline. So let me show you an example. So an example. So just again, take our friend the binary tree. And now what you do, this is an example with Gadi Cosma. There are simpler examples, but this example is useful from what I'm going to say. So let's do something like this. So we take a level, and in each level, in level, say this is level 0, level 1, level 2, level 3, level 4. In level n, we have 2 to the n vertices. 2 to the n vertices. And what we do is just we take a family of expanders, Gn of size 2 to the n, a family of expanders. So should I define what is an expander?
I think it has been defined.
Okay, cool. Yes, so just what I do is I take Gn and I just in some arbitrary way draw it on level n. So I just add edges at level n for each n so that the resulting graph here is an expander. These are bounded degree uniform expander, bounded degree of, this is part of the definition, uniform expander. So this is my graph. So one can actually give explicit example which are maybe even easier to analyze. But what we say is that if on infinite sequence of layers you put the induced graphs on each level is an expander, you add edges so that the induced graph on each level is an expander, this graph will be Liouville. So, of course, this graph is non-amenable because the binary tree is non-amenable, and what we did is we only added more edges. And now how do you show that this graph is Liouville? So naively, I will not prove it. The proof is simple yet delicate. And it appears there is a note with Gadi Cosma called non-amenable Liouville graphs, which I will send you. I will give you homework related to the one-page proof there, so you can. And it's in the archive. So the idea is that once you put here expanders, then it mixes. There are no directions to infinity. The fact that random walks start here or here, after making some jumps each time in the expander, it's eventually it forgets the history. Or if you want, you look at the harmonic measure here for this random walk, and then you compare it to the harmonic measure here. So the random walk is like acting like an operator that is further averaging the measure in L1, and then you can also show by that it also uniformly contracts the measure in L2. And this is how you can show that such a graph gives you an example of a non-amenable yet Liouville. Now again, this graph is very far from a graph. Now what I want to say now is actually coming back to the talk of Miklos. So for unimodular random graphs, or if you want limits of finite graphs, non-amenability implies non-Liouville. And in particular, in two works, one with Nicolas Courien and another work by this, okay, this is one work, and the other work is by Carrasco Piaggio. This is one person, and the other one is Pablo Lesso. By these two works, we know that Liouville property on unimodular work, from these two works, for unimodular on this setup, unimodular random graph, Liouville property is equal to zero speed. So Kaymanovich-Verchik 83 holds for unimodular random graphs. And with Nicolas.
Itai, it's Lessa, not Lesso.
Lessa. Oh, sorry, Pablo Lessa. Sorry. Yeah. So Piaggio and Lessa proved that if you have positive speed, you have non-constant bounded harmonic function, and Nicolas Courien and me, we proved that if you have zero speed, you are Liouville. Now, this idea was used recently by Justin Salez in a very nice work. He solved a long-standing, a 15-year-old question, whether there can be expanders family, with what is called with non-negative Olivier-Ricci curvature. So I will just review it quickly, but what was his idea of proof? So Ricci curvature implies the doubling property, but it is not known that Olivier-Ricci curvature for graph imply doubling property for graph. So Justin Salez's great idea was, let's take a local limit of the sequence. Say I have a sequence of graphs which has a non-negative Olivier-Ricci curvature, yet there are expanders. So what he was able to show that if you have a sequence of graph with non-negative curvature, then they must be Liouville. On the other hand, if you have a limit of the limit is unimodular, and he showed that the random walk of it must have zero speed, and it's Liouville. On the other hand, if you have a limit of expander, then it must be non-amenable, and then it must be non-Liouville. And in that way, he was able to solve this I don't know, 15-year-old question of Emmanuel Milman and Asaf Naor about whether there are expander with non-negative Olivier-Ricci curvature. Now, I would like to play the same game I have the following question. For years I'm asking the following since the 90s. I believe this is a conjecture. There is no sequence. I have time for my punchline. Yes. There is no sequence of finite bounded degree graphs Gn growing in size Gn going to infinity, so that all induced balls are expanders. So if you take typical
I just have
expander,
a question here. Sorry.
so
This is a question about the previous slide. So when you were talking about the non-availability implies durable property. So you're talking about two classes of graphs, unimodular random graphs and BS limits. So I'm
no,
just wondering which
no,
one.
it's one of the biggest open problem whether there is a unimodular graph which is not a limit of finite graphs.
Right. So that's what my question was. For which class of graphs were you referring to?
Sorry?
So when you wrote down that property,
No,
which
the property holds for unimodular random graph. I just wanted to say for people that in particular include the limits of finite graphs. Okay, so I have this question. I believe that there is no sequence of growing expanders that are expanders at the same times at all balls. So if you look on the typical random graphs, random deregular graph or Manutian graph, small balls, if you take a Manutian graph, they have gears proportional to the diameter. So graphs of balls of radius less than half the diameter or less than half the gears, they look like trees, which are very, very poor expander. Growing trees are not expanders. So I want to exclude this, and here is a strategy, and the strategy will just will need the missing part for the strategy is just doing the following. Well, first of all, I'm happy to relax that there are no sequence of graphs in which all the links are uniform expander. And what is a link? If I have a graph, some graph and a vertex, I look at the ball of radius r, then I look at the boundary of the ball, and I look at the graph, just the induced graph on this boundary. So the R link of V, so I look at the ball of radius R, and I look at the boundary, and I look at the graph on the boundary. So if my graph is a tree, the R link has no edges at all for any R. Now, I believe, I want to show that there is no graph. I mean, this will fit more this Saleh's strategy. I want to show that there is no graph in which all the links for all the vertices give you uniform expanders. So what will be the strategy? So the strategy is, first I showed you this Benjamini Cosma, this graph where you put expanders and you kill the Liouville property. So this seems to generalize very easily to other graphs. But what I would like to know, which I will really be happy if you can go even to the proof here and extend, assume G is non-amenable unimodular random graph. And the R links of the origin are a uniform expander family, then G is Liouville. So what I'm saying is just I want this instead of binary tree. Instead of binary tree, I have here a unimodular. I have here a unimodular random graph, and I'm just telling you that for every R or for an unbounded sequence of R, this is the origin of the unimodular random graph. It's a rooted graph. I look on just on the links. This is the R link here. It's a uniform expander. So can you adapt or can you show that this must imply that this graph is Liouville? This is something actually okay. So I want to just to follow the Salez trick. I want to say assume we have let's simplify. We have Gn, a sequence like that with Gn going to infinity, such that all induced balls are expanders. And here I add, which I think it will always, since most of if a ball is an expander, it seems that also the link or bounded neighborhood of the link will be an expander because everything is near the boundary of the ball. And but let me just add it as a condition, and all R links are uniform expanders. Let's take limit. Then the limit is non-amenable, just in the Salez thing. But if the generalization of this construction from BK holds, then it is also Liouville. Contradiction. Okay, so I'm stuck with this problem like 25 years now, and it seems that this random graph, unimodular random graph and graph limits will be very useful, but the only thing is we just need to show this. The extension of the proof is very simple. If you look at the BK, the proof is very simple. It's 3/4 of a page, but somehow I don't know. Maybe one can see how it generalize further. Okay. Actually, this was the punchline. I can say, oh, sorry. Okay, I will mention just another formulation or another version is that another version is that BS limits of balls in Cayley graphs, say, let's restrict even to Cayley graph, is amenable. Also, all the example, if I take balls, all the examples I know of balls, if gamma is non-amenable, all examples I know of limits of balls. No. Well, it seems that this notion of taking limits of balls in Cayley graph and to understand for which group the limit of balls is Liouville or for which balls it's recurrent, it's totally unclear. Now, another question, I was in Miklos' talk and he was talking about no, you know what? Maybe I'll stop here. Okay.
Okay. Yeah. Okay. Thank you very much, Itai, for a very exciting, very entertaining talk. Any questions? Yeah, please feel free to go ahead and ask questions. I think some people were planning to ask questions during the talk. You can ask questions now.
I have a small question. I'm Leonid Potyagailo. Do you hear me?
Yes, yes.
So the question is, suppose I have a quasi-isometry of a group. Take a Cayley graph. Can I extend this quasi-isometry to the Martin boundary? For example,
I'm not the one to answer this question.
It may be close to your theory.
Yes. Yeah, but I'm looking maybe Poisson boundary, and I don't know what is there a metric there at all? I don't know.
Yes, it's a green metric. Yes.
Yes.
So it's a function boundary with respect to green metric.
Well, I'm not. I know that the problem is hard and was considered by several non-trivial in mathematical standard group of people, and it's still open many years now.
Mm-hmm.
Yeah. Go ahead.
I was just going to say that generally the Martin boundary is much harder to understand than the Poisson boundary. So trying to do that as some kind of reduction doesn't seem like a good idea. I mean, I think maybe things about the Martin boundary should be true, that they're preserved by changing the generating set, but I think that should be much harder than the questions about the Poisson boundary.
So what is harder? Sorry.
Generally, the Martin boundary is just a much less well-behaved object than the Poisson boundary. So.
Okay.
So one more question for Itai. So where you construct this this example with Gary Cosma, so that example looks a lot like constructing some kind of a warp product in a Riemannian setting. Is there a sort of a more geometric analog? I mean, is there a geometric version of the same question?
It looks you have indeed these two directions, but
right.
But if the only thing I can say is that if you take these expanders to be with very large girth, then locally it looks like a tree. This is the only comment I have to say, that locally this graph, as you say, walk along or go towards infinity, larger and larger neighborhood of you look like a tree. So I suspect there are some maybe a Riemannian version like this. It's a question whether this such graph can be realized as like my colleague Tzachi Gelander, he would like to understand if you take G mod gamma in higher rank, and where the G mod gamma is non-compact. And then the question is whether such object can be realized as G mod gamma. I'm not the one to answer, but he wanted to show that G mod gamma contain non-constant bounded harmonic function. I just asked him first show that such object, you cannot realize such object as G mod gamma.
All right, so let's thank Itai, and wish we had a longer course, and maybe at a future date. Thank you very much. Thank you very much.